Good morning, guys. We're going to finish up lesson 7.1 today, integrals as net change. And today is going to look a little wonky at first here. We're going to be talking about a car moving with an initial velocity of 5 miles per hour, accelerates at the rate of, and remember, dv dt, that's the rate of change of velocity, which is acceleration, because it's a of t, and that equals 2.4 t in miles per hour seconds for 8 seconds. Now, this unit of measure may be really weird for you, mile per hour seconds, but if you think about this, it might be important in like maybe a crime scene investigation to find out mile per hour seconds or find out how fast, just different, I don't know even how to explain it, but it's just a wonky unit of measure, okay? And what we want to find out here, what we are looking for, is we want to know how fast is the car moving when the 8 seconds are up, okay? So remember, if I have a of t, well, what do? Well, how do I find out how fast I'm going? How fast I'm going is actually velocity, is it not? It's the positive aspect of velocity. Okay, and think about this. If I had a graph, okay, and here's my a of t graph, here's my acceleration graph, and I know this is my t-axis for seconds, okay, and what happens is my acceleration is given to me in miles per hour seconds, okay, and so if I am coming across here and I am accumulating, okay, underneath, if I'm accumulating underneath my acceleration curve, finding area, what I'm doing is I'm taking miles per hour seconds times seconds, which are going to give me miles per hour, all right? Miles per hour. We might have some conversions we need to do here. And that mile per hour seconds is a weird unit of measure. But if I accumulate acceleration, it gives me velocity. Okay, so how far or how fast is the car moving when the 8 seconds are up? Well, I need to accumulate my velocity from 0 to 8 to answer that question. So, but check this out. This is weird because this has an initial velocity of 5 miles per hour. And if I wanted to find out my velocity, well, remember, it's going to be my initial velocity plus my accumulated velocity from 0 to 8 of a of t dt. That is going to give me my velocity accumulator. Okay, that's going to accumulate all the velocity I have. Okay, so how would I do this? I would actually do this pretty simply because I know 5 plus my integral from 0 to 8, and I know a of t is 2.4 t dt. Well, I could easily figure this out because this is an antiderivative that's pretty simple for me to know. Well, it's going to be 5 plus, if I accumulate that, well, that's going to come from a t squared, and 2 times what gives me 2.4, so that's a 1.2. And I'm going to evaluate that from 0 to 8, okay? So what happens is, this is going to be 5 plus, please don't forget, accumulate, okay, top minus bottom, and the 8 goes in there, so that's really 1.2 times 8 squared minus 0, and 1.2 times 8 squared, so in the end, this would be 5 plus 1.2 times 8 squared, and that's going to equal what? Well, 81.8 miles per hour. Okay, so that is your speed at 8 seconds. And notice, this one had an initial velocity of 5 seconds. So I started out at 5. T equals 0, I was already going 5 seconds. Okay, so how fast is the car moving when the 5 seconds are up? Well, it's moving 81.8 miles per hour. Well, remember, we can do this in a few different ways on our calculator, too. Okay? So if we were looking at our acceleration, Okay? And from our acceleration, we could look at our velocity. So if we wanted to accumulate our velocity curve, A of t actually equals 2.4 t. So if I wanted to look at that little bugger, I could integrate that, right? I can find that antiderivative real easy and make this work in my calculator. Okay, so bottom line, what I'm trying to come back here is that this problem, okay, if they gave me a really ugly acceleration problem, okay, that was not an easy antiderivative to find, what would I do? Well, what I would do would be I would come to my calculator and I would graph that acceleration function, okay? Now, I want to be able to see this whole function, so I want to be able to get my windows. I only need to see really 0 to 8, so 0 to 10 is good. But if I went 0 to 8, what's 2.4 times 8? Well, to see my upper bound, well, it's probably going to be around 20-ish, so I'm going to change my windows here so I can see everything, my window settings, and I'm going to just go from 0 to actually, I'm going to go 10. It doesn't really matter. 0 to 10. Scale of 1. And I can see I'm going to go from 0 to, what's my max we said? Probably about 20. And I'm going to go scale of 1. I hit enter. So I can see my 8 in there. Right? So 8 times 4, well, that's 16, or no. So I should be good there at 20. And if I needed to accumulate from 0 to 8, what I can do is I can say analyze my graph. We are going to do an integral 7 with a lower bound of 0 and an upper bound of 8 seconds, and it's going to accumulate that area. Okay? So if I took this window, oh, I don't want to do that. I want to take my tool, I'm going to capture that page, and then I'm going to come right back to my notebook, and I'm going to paste that little bugger in there like I did yesterday. Well, what we just found is if it was an ugly function, and that was my A of t function, well, I just accumulated, in the end here, I just accumulated 76.8 miles per hour, because here's my miles per hour seconds times my seconds. That's going to give me miles per hour underneath the curve. And that's what I accumulated from 0 to 8, plus my 5 that I started with. That's going to give me my speed of 81.8 miles per hour. Okay? So if I took that's another way to get it. Well, if you're like, I don't like, this is a really important integral to be able to write right here. And if you're like, oh, I keep forgetting how to do that, well, please try not to, because it's going to be pretty important. But I don't have to do it that way, because there's another way to do this. If I know A of t equals 2.4 t, I know the integral of A of t is V of t, which is going to give me my 1.2 t squared plus c. And if I know my acceleration at 0 equals 5, right, that's going to give me 5 equals 0 plus c. V of t is going to equal 1.2 t squared plus 5. And if I need to know what this is going to be, if I need to know my speed, because here's my velocity, so if that's my velocity, all I need to know what's my velocity at time 8. Well, it's 1.2 times 8 squared plus 5, which is exactly what we did up here, just in a little different manner, right? And what are we going to get? We're going to get 81.8 miles per hour. Okay, so I'm just accumulating my velocity to find my speed. Well, how far did the car travel in those 8 seconds? Well, we want to answer in miles and feet, okay? And what do we know? Well, this is kind of weird, because now how far did the car travel in those 8 seconds? So we want to know what's the total distance traveled. Okay, so my total distance traveled, well, I got a few ways to do that again too. Well, and if I'm looking at my v of t function, and I know that's 1.2t squared plus 5, well, I could actually graph that little guy. Okay, pretty simple. I got a y-intercept here at 5. It's a quadratic opening up, so it's going to look something like that. And I need to accumulate from 0 to wherever 8 is. And if I accumulate underneath my velocity curve, okay, these are still seconds, and this is miles per hour. What units? What is that going to give me here? It's going to give me mile per hour seconds, because I got to multiply these. It's going to give me miles per hour seconds. Okay, so I'm going to have a conversion I'm going to have to do down here at the very end. Well, there's two ways to skin a cat. My total distance, okay, my total distance, I can take my integral from 0 to 8, absolute value of v of t, dt, and that's going to give me my total distance traveled. However, I'm going to type that into my calculator back here once now. So I'm going to come back here, I'm going to come here, and what I want to, actually, no, I don't want to go there. I'm going to add a new page. I'm going to come back. I'm going to add a different calculator page. And I want to do a menu 43. We're going to go from 0 to 8 of my absolute value of 1.2 x squared plus 5 dx, right? And when I do that, that's going to give me 244.8. 244.8. These are weird units now, okay? 244.8. But now, remember, these are going to be 244.8. Those are going to be miles per hour seconds, okay? And what do I want to be? I want my answer. I just want my answer in miles first. And once I get miles, I can convert to feet. So what do I need to do here? I need to do a little bit of a dimensional analysis to find out. I need to do a little dimensional analysis here to find out how many miles I traveled. So what am I going to do there? Well, I want my 244.8. I got miles per hour. And what do I need to multiply this by? I want to kill my hours. Oh, hold on. That's bad, Bill. I want seconds, okay, over 1. So first and foremost, I need to get rid of hours, so I'm going to multiply by 1 hour here. And I need to get rid of seconds, and so these are going to be seconds, but this needs to be like 3,600 seconds in an hour. So if I did that, I take my 244.8 divided by 3,600, this is going to be miles when I convert this, because my analysis cancels out my time and I just have miles. So if I came back to my calculator and I said divided by 3,600, what do I get? About 0.068 miles, okay? That's going to take me to equals 0.068 miles. That's how far we traveled in that 8 seconds. Well, hopefully that makes sense. Well, that's in miles, and we also want the answer in feet. So we would take this times 5,280 feet in a mile, and that's going to convert me to my feet. So I come back here and I say times 5280. Please give me my answer. 395 or 359.04 feet. So 359.04 feet would also be my answer there. Okay. Well, you have to convert that answer. Okay, because because you need to know when you integrate, it's really important to know what units are coming out of it, because you're multiplying the units on your x and your y axis. And so in that case, we're getting mile per hour seconds. And we know logically, if we're trying to find out how far we traveled in miles and feet, they're telling us that. Well, we need to make sure our units, we need to do some dimensional analysis to make sure what units need to cancel, okay? And you guys know how to do all that. Well, if it were a really disgusting integral, okay, well, I could still come back to my calculator here, I think, and I could do a menu 43, and I could say 0 to 8, and I could do my, well, I just did that. Why am I doing that again? Because I already have that in there, so I don't need to do that again. What was the other thing I was looking at? Well, that was pretty much it. The other thing I could do is if I needed to know, well, I could probably, it'd be a little bit more tedious, okay? I could come back and I could actually find out, I could take my velocity function here, okay? If they gave me an initial velocity, but they really did, or an initial position, which they didn't, so I don't know how far I traveled, right? So in those 8 seconds, so I'm assuming it's at 0. So if I integrate that, that should give me my position function, and I should be able to plug 8 in there and get my position function, but that's going to be in miles, which would then need to be converted, hopefully, to feet and all the good stuff there, okay? So that's just some unit analysis. The very last problem we're going to go through here, and this one seems kind of complicated, but this is like an old AP problem, but we have a consumption net change problem. And a pump connected to a generator operates at a varying rate depending on how much power is being drawn from the generator to operate other machinery. The rate in gallons per minute at which the pump operates is recorded at 5-minute intervals for 1 hour in the chart below. What they want to know, okay, they want to know how many gallons were pumped during the hour, okay? So what I always did, okay, I always looked at the units they gave me, and I thought, how do I take these units and make these units into, do I either multiply my units here, or do I divide my units to get the units of my answer? Well, if I took the rate of gallons per minute times minutes over, well, that's going to give me gallons, and that's really what I want, okay? And if I took my gallons per minute and I divided by minutes, okay, over 1, well, that's going to give me gallons per minute squared, which is going to kind of be looking like an acceleration. They want gallons. If I'm multiplying my units to get the appropriate units, that means it's going to be an integral, not a derivative. Over here would be a derivative when I'm dividing my units, because it's giving me a rate of change then, okay? So I knew it's an integral. So when I'm thinking about this, and I don't even have to think overly hard on this, because they want me to estimate the number of gallons that were pumped using 12 trapezoids of equal width. Well, the only thing we did with trapezoids, guys, was area approximation. So if I'm thinking about my trapezoidal rule, I really don't want to waste my time to make a big old graph of all this data that they gave me of all these points coming up and finding all these trapezoids in here, okay? I really don't want to waste my time to do that, because I know my trapezoid using 12 trapezoids is going to equal, well, we need to remember, how do you find the area of a trapezoid? It's 1/2 the height times the sum of the bases, remember? And that's where we took our first one. We took our first height, our y sub 0 plus, and then 2 y sub 1s plus 2 y sub 2s plus ... plus all the way down to 2 y sub n minus 1s plus a y sub n. because we only used that first leg once, but then each leg beyond that was shared on all these different trapezoids. Equal width, I can see my width between each time interval here is 5. That 5, that's my horizontal distance, that's my height. So my trapezoid, using 12 trapezoids, is going to equal 1/2 times my consistent equal height of 5 times. Now, really write it out, because I had people, oh, I didn't know I had to write them all up. Well, that's why you got the wrong answer, because you lost some of your answers in there. But we take the first one, and we're going to say the first one plus 2 of everybody else in there. Okay, there's 1 of the first, 1 of the last, and 2 of everybody in between. That's 64 plus 2 times 58 plus 2 times 57 plus 2 times 55 plus 2 times 55 more plus 2 times 59 plus 2 times 60 plus 2 times 60 plus 2 times 63 plus my last one of 63. And notice when I look at all of these, when I'm thinking I got a first one, shared, how many legs, how many different values should I be summing up in the middle with 12 trapezoids? Well, if I have 12 trapezoids in the middle, like here, right here, I got 1, 2, 3, 4, 5 trapezoids. I have 1, 2, 3, 4, 5, 6 values inside. So if I have 12 trapezoids, I'm going to have 13 values in here that are getting summed. So I'm 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I got them all. That's how many I should have. I go straight to my calculator. Okay, I'm gonna sum those up, and I'm gonna say T, my 12 trapezoids, is going to actually equal 5/2 times the sum. When I sum all those up in there, I get 1,433. And when I multiply that out, that's going to be 3,582.5 gallons. Okay? And that would be how many gallons were pumped over the hour. Okay? How many gallons were pumped during the hour? 3,582.5 gallons were pumped during that 60 minutes. Okay? So next thing I'm going to do here is, I'm not expecting you to do this, but we're going to use a sinusoidal regression model. AP test is not going to make you do this. That's why I have this prepared in here. I don't know if you remember back to Algebra 2 when we did this regression stuff, but all I did is I went to my tables in my calculator and I set up my time and my rate, and I made up all those ordered pairs. I then took that and I regressed it, or I made a scatter plot of it, and I changed my windows nice so that when I stretched it out and I saw vertical shifts and all that good stuff, I could see my sinusoidal. I did a sinusoidal regression in there. I can see that sinusoidal regression fits those data points pretty stinking good. In my calculator, actually, there's more over there. And what I did was I just wrote down what the sinusoidal regression model was, and I called it G of T. Okay, so that's what we did. So G of T is the number of gallons being pumped at any particular time right there, okay? So that is my G of T, and that is my gallons per minute rate that I'm coming. So we're calling that. So if we're going to use G of T found in Part B to estimate the number of gallons in a 1 hour period, we would simply take the integral from 0 to 60, because this is in minutes, okay? Because we're in minutes, my limits should be in minutes here of G of T dt. And when I type that into my calculator, okay, which I did already, and when I type that into my calculator back here, okay, there's my sinusoidal function. G of T is 4.122 times the sine of 0.146x minus 0.072 plus 58.955 dx. Okay, this is why we need to be able to evaluate these in our calculators. I don't want to find the antiderivative of that. It's going to take time. And all of these numbers here, they are all rounded to the nearest 3 decimal places, okay? And if I use the rounded and I approximate, and I find the integral from 0 to 60, I'm finding out there's about 3,000 or 3,586.3705 gallons being pumped. So if I capture this page here, and I bring this page, not there, and I bring this page back here, I didn't want to do that. I'm going to go back, so I'm going to edit, and I'm going to paste, and I'm going to take this little guy, and I'm just going to say, hey, that integral actually equals what I said right there, okay? This, and if I rounded it, the decimal places is going to be 2,586.370 gallons, okay? Ooh, 3,000, not 2,000, 3,586.37 gallons, okay? And then if they came down here for the last one, and they wanted me to find the average rate of the generator. That is my average number of gallons pumped over the 60-minute period. That is my average value theorem. If you remember that, that's my 1 over b minus a times my integral from a to b of f of x dx. Okay? So if I did that, to find my average, all I got to do is take this, divide it by the number of minutes. Well, that's going to be 60 minus 0. So if I took this answer and divided it by 60, what that's going to give me is the average rate per minute. Or the average rate is going to be, and remember, this integral right here is going to output gallons. And if I divide that by my time, I'm going to get gallons per minute. Okay, that's going to give me my average of gallons per minute. So if I came back here and I said divided by 60, and I took that, I'm getting 59.773. 59.773 gallons per minute. That would be my average value across the interval. They're going to make you find average values as well. Okay? So that sums up our 7.1 integrals as net change. You should be able to tackle all the homework in there. Please let me know if you got questions. And we will be back tomorrow with area between curves, I think. Have a good rest of your day.